Assalamu alaikum. We continue talking about chapter 4, part 2, and after we talked about primary and secondary structure of protein, today we want to continue talking about tertiary and quaternary. The tertiary structure of protein refers to the three-dimensional arrangement of all atoms in a molecule, which includes the conformation of side chains and the positions of apocytic groups. In a fibrous protein, the shape is a long rod, and the backbone of the protein does not fold back on itself. The arrangement of atoms of the side chain is not specified by the secondary structure. However, in a global protein, the tertiary structure helps determine the way helical and pleated sheet sections fold back on each other. Interactions between the side chains play an essential role in the folding of proteins. Now, what are the kind of forces that tend to stabilize the tertiary structure or involved in tertiary structure? When we talked about primary structure of protein, we said it's stabilized by peptide bond, whereas in the secondary structure, it's stabilized by hydrogen bond. Now, the forces involved in tertiary structures are many, and they play a role in holding protein together in its correct native conformation. Some of these forces are covalent and many are not. The primary structure of protein depends on the formation of peptide bonds, which are covalent. Higher order levels of structure, such as conformation of the backbone, secondary, and the position of all atoms in the protein, tertiary structure, depend on non-covalent interaction. If the protein consists of several subunits, then the interaction of the subunits also depend on non-covalent interaction. These non-covalent stabilizing forces contribute to the most stable structure for a given protein, the one with the lowest energy. Now, what are the forces? Let's see. First, we have backbone hydrogen bonding between polar side chains of amino acids, hydrophobic interaction between non-polar side chains, electrostatic attraction between side chains of opposite charge, complexing several side chains to a single metal ion, and all these, 1, 2, 3, 4, these are non-covalent, and the only covalent force is the disulfide bonds between the side chains of 2-cysteine residue, which restrict folding patterns available to polypeptide chain, absent in myoglobin and hemoglobin but present in chymotrypsin and trypsin. Now, if you look at this schematic representation of the forces that stabilize the tertiary structure of protein, here we can see, here we want to start with the covalent type of forces. You see, this is when you have 2 cysteine residue close to each other, they form disulfide bond. This is covalent. Now, we have hydrophobic interaction with non-polar side chains close to each other. We have metal-ion coordination. Here we have side chain hydrogen bonding to distinguish it from backbone hydrogen bonding in the alpha helix, the secondary structure. And here we have electrostatic attraction between oppositely charged R groups. So by looking at this schematic representation, you can memorize all these forces. How people were able to determine the tertiary structure of protein? The experimental technique used to determine the tertiary structure of protein is called Xray Crystallography, which uses a perfect crystal in which all individual protein molecules have the same three-dimensional structure and orientation. When a pure crystal is exposed to a beam of X-rays, a diffraction pattern is produced. This pattern results when electrons in each atom scatter the X-rays. These scattered X-rays can reinforce or cancel each other, giving a characteristic pattern for each molecule. Information is extracted by a mathematical analysis called a Fourier series. Don't worry about the information here. the detailed information about X-ray crystallography, note that this technique was used to determine the tertiary structure of myoglobin, which now we want to talk about, and we take myoglobin as an example of protein structure. It consists of a single polypeptide chain of 153 amino acid residue and a prosthetic group heme in a hydrophobic pocket. The heme is iron-containing cyclic compound, has a compact structure. Myoglobin has 8 alpha helical regions, which are designated A, B, C, D through H, and they are stabilized by hydrogen bonding in the polypeptide backbone. Beta-pleated sheet regions are absent from myoglobin. Exterior contains most of the polar side chains. Interior contains non-polar side chains and 2 polar histidine residue that are involved in interactions with the heme group and with bound. So again, myoglobin has 8 alpha helical region and no beta-pleated sheet. Approximately 75% of the residue in myoglobin are found in these helical regions, which are designated again by letters A through H. Hydrogen bonding in the polypeptide backbone stabilizes the alpha helical regions. Amino acid side chains are also involved in hydrogen bonding. And if you look at this is the structure of myoglobin. Note that the peptide backbone and the heme group are shown overlain on the space-filling model. The helical segments are designated by the letters A through H. This is H. And here A. So we have 8 of them, A through H. The terms NH3 and COO minus indicate the N-terminal and C-terminal ends respectively. So here you can see this is N-terminal and this is C-terminal. And here in red you see the heme group. Now, what is the heme group? The heme group consists of a metal ion, iron 2, a metal ion, and an organic part, protoporphyrin 9. The notation iron 2 refers to Fe plus 2 when metal ion occurs in complexes. Now the porphyrin part consists of 4-5 metal ions. The porphyrin part consists of 4 5-membered rings based on the pyrrole rings. This is the pyrrole ring, so you bring 4 of them connected by methane bridges here. Okay. To form a square planar structure. Now the iron 2 ion has 6 coordination sites here after we add. So after we add iron 2, it becomes heme. So heme is protoporphyrin 9 plus iron. So it has again 6 coordination sites and it forms a 6 metal ion complexation bonds. 4 of the 6 sites are occupied by the nitrogen atoms of the 4 pyrrole type rings of the porphyrin to give the complete heme group. Now the presence of the heme group is required for myoglobin to bind oxygen. So these are 4 sites. So this is required for heme to bind oxygen. Now the 5th coordination site, which is here, of iron 2 is occupied by one of the nitrogen atoms of the imidazole side chain of histidine residue of 8. F8 refers to the 8 residue in helical segment F. This histidine residue is one of the 2 in the interior of the molecule, and the oxygen is bound to the 6th coordination site of the iron. The 5th and 6th coordination sites lie perpendicular to and are opposite of the plane of the peripheral ring. Now the other histidine called. So here we have, this is histidine F8 occupies the 5th coordination site, and the 6th coordination site is left to bind oxygen. Now we have also another histidine residue is found in the interior of the molecule called histidine E7. The 7th residue in helical segment E lies on the same side of the heme group and as the bound oxygen. Now, this second histidine is not bound to the iron or to any part of the heme. As you can see, it is free. But it acts as a gate. It acts as a gate that opens and closes as oxygen enters the hydrophobic pocket to bind to the heme. Now, the E7 histidine sterically inhibits oxygen from binding perpendicularly to the heme plane with biologically important ramifications. Now, the affinity of free heme for carbon monoxide, CO, is 25,000 times greater than its affinity for oxygen. When CO is forced to bind at an angle, then its advantage over oxygen drops by 2 orders of magnitude. CO is a potent poison. Here you see histidine E7 forces oxygen to bind in an angle, not perpendicular, so that it will be released later. Now let's talk about the concept of denaturation and refolding. Denaturation refers to the unraveling of the three-dimensional structure of a macromolecule caused by the breakdown of non-covalent interactions that can result from heat, large changes in pH, which alter charges on each side chains, detergents such as sodium rhodesyl sulfate, which disrupt hydrophobic interaction, urea and guanidine hydrochloride, which disrupt hydrogen bonding. If the protein contains disulfide bond, then we need this chemical called beta-mercaptoethanol to reduce the disulfide bridges to 2SH groups. So if we look at this figure, shows us denaturation of protein. This is the native conformation and this is the denatured conformation. They found that the native conformation, however, can be recovered when denaturing agents are removed. And this is an experiment carried by one of the scientists, which he worked on, a scientist called Atkinson. He worked on the native ribonuclease. This is the native conformation. He used urea, he added urea and added beta-mercaptoethanol, and then you have here your denatured protein. Urea is added to the reaction to facilitate unfolding and to increase accessibility of the disulfides to the reducing agent. And then the native conformation can be recovered by removing mercaptoethanol and urea, and this is called refolding. We conclude that some types of denaturation can be reversed, while others are permanent. Now we come to the so-called quaternary structure of proteins. Pertains to proteins that consist of more than one polypeptide chain. Each chain is called a subunit. The term oligomers, molecules that are made up of the number of smaller subunits, include dimers, trimers, tetramers. Chains interact with one another non-covalently via electrostatic attractions, hydrogen bonds, and hydrophobic interaction. Now, proteins that can exhibit this property called allosteric. Not all multi-subunit proteins exhibit allosteric effects, but many do. And a classic illustration of the quaternary structure and its effect on protein properties is a comparison of hemoglobin and allosteric protein with myoglobin, which consists of a single polypeptide chain. Now both hemoglobin and myoglobin bind oxygen reversibly, but the binding of oxygen to hemoglobin exhibits positive cooperativity. What does this mean? Whereas oxygen binding to myoglobin does not. which means binding of one oxygen facilitate binding of the other oxygen to the protein. Now let's talk about hemoglobin. Hemoglobin is a tetramer with two alpha chains, each one 141 amino acid residue, two beta chains, each 146 amino acid residue long. The overall structure alpha 2 beta 2. Most amino acids of the alpha chain, beta chain, and myoglobin are homologous. Now, oxygen binding of hemoglobin. One molecule of myoglobin binds one oxygen. Hemoglobin can bind up to 4 molecules of oxygen. Now, binding of oxygen to hemoglobin exhibits positive cooperativity. When one oxygen is bound, it becomes easier for the next oxygen to bind. How does the hemoglobin work? Now, the two different types of behavior exhibited by myoglobin and heme are related to the functions of these proteins. Myoglobin, its function is oxygen storage and requirement binds strongly to oxygen at very low pressure. Saturation 50% at 1 torr partial pressure of oxygen. So at the peripheral tissue like in muscle, the pressure is 20 torr and P50 for myoglobin is 1 torr. Whereas hemoglobin function oxygen transport requirement binds strongly to O2 and release O2 easily, and the saturation 100% when oxygen pressure is 100 torr. Now let's look here at this figure which shows us the structures of the oxyhemoglobin and oxyhemoglobin. Note the motions of subunits with respect to one another. There is much less room here at the center of oxyhemoglobin than in the deoxygenated hemoglobin. So here the two beta chains are much closer to each other in oxygenated than in deoxygenated. And the change is so marked that these two forms of hemoglobin have different crystal structures that can be seen here. Now, other ligands are involved in cooperative effects when oxygen binds to hemoglobin. Both H plus and CO2, which themselves bind to hemoglobin, affect the affinity of hemoglobin for oxygen by changing the protein's three-dimensional structure in subtle but important ways. Now, the effect of H plus is called the Bohr Effect. So, the effect of H plus is called the Bohr Effect after its discoverer, Christian Bohr. The father of physicist Niels Bohr. The oxygen binding ability of myoglobin is not affected by the presence of H plus or CO2. Now, an increase in the concentration of H plus, which means lowering of the pH, reduces the oxygen affinity of hemoglobin. Increasing H plus causes the proteination of key amino acids, including the N-terminals of the alpha chains of histidine, 156 of beta chains. Now, this histidine is stabilized by a salt bridge to aspartate 94, which favors the deoxygenated form. Now, table 1 here summarizes the important features of the Bohr effect. You should understand this. Now, what happens in the actively metabolizing muscle, which they release H plus, so H plus increases and pH is lower. Hemoglobin affinity for oxygen is decreased and it releases oxygen and hemoglobin binds H plus. What happens in the lungs, where we have low H plus, higher pH and plenty of oxygen, so hemoglobin binds oxygen and hemoglobin releases H plus. So oxygenated form of is a stronger acid since it has a lower pKa than its oxygenated form. Deoxygenated hemoglobin has higher affinity for H plus than the oxygenated form. and this is found in the actively metabolizing muscle. When after hemoglobin releases O2, it becomes deoxygenated mannitol. This has higher affinity for H+, and it binds H. Now this figure shows you the oxygen saturation curves for myoglobin and hemoglobin at different pH values. Notice here, as the pH decreases, the curve becomes sigmoidal. Hemoglobin in blood is also bound to another ligand called 2,3-bisphosphoglycerate, BPG. The type of binding is electrostatic because this is a highly negatively charged small molecules. It will interact with the side chains of basic amino acids, so we expect the type of binding is electrostatic. Now, in the absence of PPG, oxygen binding capacity of hemoglobin would be higher. P50 equal 1 torr, and little oxygen would be released in the capillaries. PPG plays a role in the supply of oxygen to the growing fetus. PPG is known as an important allosteric effector of hemoglobin. Fetal hemoglobin has a higher affinity for oxygen than adult hemoglobin. Here, if you look here at this figure, which shows us the binding of PPG to deoxyhemoglobin, note here the electrostatic interaction between the PPG and the protein. And here you see the positively charged R group of basic amino acids. They found that, so here if we strip hemoglobin from PPG, then we will see this. This is the oxygen binding curve for hemoglobin with PPG, normal sigmoidal allosteric type of curve, but when it's stripped from PPG, P50 decreases to 1 value. Now P50 here is 26, it decreases to 1, and hemoglobin now resembles myoglobin, and it will bind oxygen tightly and will not release it. PPG also plays a role in supplying a growing fetus with oxygen. The fetus obtains oxygen from the mother's bloodstream via the placenta. Fetal hemoglobin, designated hemoglobin F, has a higher affinity for oxygen than does maternal hemoglobin, allowing for efficient transfer of oxygen from the mother to the fetus, as you can see here in this figure. Here, in blue, this is the adult or maternal hemoglobin, and in red, the fetal hemoglobin. You see here O2 flows from maternal oxygenated hemoglobin to fetal deoxygenated hemoglobin. So you see P50 decreases, which means fetal hemoglobin has higher affinity for oxygen than its mother. Now, two features of fetal hemoglobin contribute to this higher oxygen binding capacity. One is the presence of two different polypeptide chains. The subunit structure of hemoglobin F is alpha 2 gamma 2, where the beta chains of adult hemoglobin, the usual, have been replaced by the gamma chains, which are similar but not identical. Now, the second feature is that hemoglobin F binds less strongly to PPG than does hemoglobin A. In the beta chain of adult hemoglobin, histidine 143 makes a salt bridge to PPG. In the beta hemoglobin, the gamma chain has an amino acid substitution of serine for histidine. So we replace the positively charged amino acid histidine with uncharged amino acid called serine. This change of a positively charged amino acid for a neutral one decreases the number of contacts between the hemoglobin and the PPG, effectively reducing the allosteric effect enough to give fetal hemoglobin a higher binding curve than adult hemoglobin.